In section 3.5, we're going to look at the algebra of functions. So we're going to look at how to add, subtract, multiply, and divide functions. And then we'll also look at composite functions. First, let's look at what it means to add, subtract, multiply, and divide functions. F plus g of x is defined as f of x plus g of x. Straightforward enough. F minus g of x is equal to f of x minus g of x. Again, no surprise here. The same is true when we're multiplying. F times g of x is equal to f of x times g of x. And finally, f divided by g, when evaluated at x, is equal to f of x divided by g of x, as long as the denominator is not 0. Let's look at some examples to show you how this works. If f of x is equal to x squared minus 16 and g of x is equal to 5x plus 15, then f plus g, when evaluated at 3, is equal to f of 3 plus g of 3. Well, when x is 3, f takes on a value equal to 3 squared minus 16. That's what f of 3 stands for. Now we're going to add that to g of 3, which would be 5 times 3 plus 15. Notice here that this first quantity is f of 3, and this second quantity is g of 3. So we're essentially substituting the value 3 into both function rules and then adding those together. Now we just have to simplify. 3 squared is 9. 9 minus 16 will give us a negative 7. 5 times 3 is 15, plus another 15 would be 30. So finally, we get a value of 21. In our second example, we have f minus g evaluated at 2. By definition, this is f of 2 minus g of 2. So we're going to substitute 2 for x into both rules, that of f and that of g, and then subtract. F of 2 is equal to 2 squared minus 16. And now we have to be very careful because we have to subtract all of g of 2. G of 2 is equal to 5 times 2 plus 15. So here, this first quantity is f of 2, and we're subtracting the second quantity, which is g of 2. So we have 2 squared minus 16, that is 4 minus 16, so that's going to be a negative 12, minus 5 times 2 is 10, 10 plus 15 is 25. Negative 12 minus 25 will give us a negative 37. When it comes to multiplication, f of g, evaluated at 5, is equal to f of 5 times g of 5. F of 5 is equal to 5 squared minus 16. I'm going to put that in parentheses because we have to multiply by g of 5, which is 5 times 5 plus 15. 5 squared is 25. 25 minus 16 is 9. In the second set of parentheses, 5 times 5 is 25. 25 plus 15 gives us 40. 9 times 40, finally, will give us 360. In the next example, we're dividing f by g and evaluating at x equals 6. By definition, this is equal to f of 6 divided by g of 6 as long as the denominator is not 0. Well, f of 6 has a value equal to 6 squared minus 16, and g of 6 has a value equal to 5 times 6 plus 15. In the numerator, we have 36 minus 16, which is 20. In the denominator, we have 5 times 6, which is 30, plus 45, plus 15, which gives us 45. So after reducing, we get 4 over 9. So adding, subtracting, multiplying, and dividing functions is equivalent to doing those same operations after substituting the given value of x. In the next example, we are going to add, subtract, multiply, and divide, except that we don't have the rules for the function f and the function g. Instead, we have their graphs. So we're going to have to read off some values from the graph to answer these questions. First, we have f plus g evaluated at 2. By definition, this is equal to f of 2 plus g of 2. So f of 2 is the y value for the ordered pair on the graph of f that has an x value of 2. Well, I know this is going to be a little hard to read, so I'm going to trace over these two graphs in different colors. In red, I'm going to go ahead and shade the graph for f. So this is f in red. And then for g of x, I'm going to shade that in green. That's a line. That's g of x. All right, let's see. F of 2. So I'm looking at the red graph, and I'm looking for an x value of 2. I found that point right here where I'm shading. So on the red graph, the ordered pair that has an x value of 2 is the one that I've just shaded in blue. And that has a y value equal to -1. Now let's go to the green graph for g. On the green graph, the ordered pair that has an x value of 2 is right here. X is 2, and in that case, y is 0. So again, there are two ordered pairs here that I'm looking at. The ordered pair 2, -1, that is on the red graph, and the ordered pair 2, 0, that is on the green graph. So the -1 is coming from the y coordinate, and the 0 is coming from the y coordinate. So those are these two values here. -1 plus 0 is, of course, -1. Now, let me erase here a little bit. Oh, I erased too much, but that's okay. I can always add it back. Let me go back and retrace the two functions. Okay. So next we have f minus g evaluated at 4. This is equal to f of 4 minus g of 4. On the red graph for f, I'm going to find the ordered pair that has an x coordinate equal to 4, and I see that that's right here at 4, 1. And I'm going to do the same thing for g. On the green graph, the ordered pair that has an x coordinate equal to 4 is all the way up here at 4, 4. So the two values that I'm looking for are 1 and 4, those y coordinates. F of 4 is 1 minus g of 4 is 4. So this is going to simplify to -3. All right, let's erase the blue dots, and let's go back and look at multiplication next. So now we have f times g evaluated at -1 for x. By definition, this is going to be equal to f of -1 times g of -1. Well, f of -1, if I look at the red graph, the ordered pair that has a value of -1 is over here, and that has -1 for x, and it looks like it has a -2 for y. And for the graph G, when x is -1, we're all the way down here at -1 for x and -6 for y. So this is equal to -2 times a -6, which is a +12. Now hopefully you see what we're doing. We're looking at which ordered pairs have the corresponding x coordinates so that we can look at those y values that belong to those x values. Next, we have f divided by g evaluated at x equals 6. So we'll start with f, which is the red graph. Which ordered pair has an x coordinate of 6? I've just highlighted it here. That is 6, 3. So f of 6 has a value of y for 3. And now let's look at the green graph. When x is 6, we are all the way here at the top. 6 for x, and it looks like 8 for y. So then 8 would be the denominator. G of 6 would be 8. And in this case, the fraction is already simplified, so that becomes our final answer. Now let's look at domains of these combined functions. To find the domain of the sum of f and g, we first find the domain of f, and then find the domain of g, and look at which x values are part of both sets, which we label as the intersection of those two separate domains. Same goes for the domain of the difference, the domain of f minus g. We first find the domain of f, then find the domain of g, and look at which x values are in both, in its intersection. And so on for the domain of the product of f and g. There is one caveat here for the domain of the quotient, for the domain of f divided by g. We not only have to look at what is in both domains, but we also want to make sure that we are never intending to divide by 0. So we want to exclude any values of x that would cause the function g of x to take on a value of 0. So let's look at some examples. If f of x is equal to 4 divided by x, and g of x is equal to the square root of x minus 6, then let's find the domain of the sum of f and g. All right, so the domain of f, let's go ahead and identify that. So for the domain of f of x, we look at which x values would cause problems. We see that x cannot take on a value of 0 because division by 0 is not defined. That means that the domain of f includes all values from -infinity up to not including 0, and then we pick up on the right side of 0. This is how we write the domain in interval form. For the domain of g, we see that we're taking the square root of a quantity. That quantity cannot be negative. Now it can be 0 and it can be positive, it just can't be negative. So x minus 6 must be greater than or equal to 0, which means that x must be greater than or equal to 6. The way we write this in interval notation is that we can start at 6, 6 is included, and go anywhere as far as we want to the right. So for the domain of f plus g, we have to see which x values are in both of these domains. Well, I'm going to go ahead and use a number line so that we can see this visually. The domain of f included everything except 0. So let me do this in red. 0 was not included, but we could have gone anywhere to its left and anywhere to its right. For the domain of g, we had to start at 6. 6 was included, and then it could have been any number to its right. So if we look at which x values are in both of these domains, basically the numbers starting at 6 and going anywhere to the right of 6. That would be the intersection. So in other words, where these two graphs overlap is right here where the left boundary is at 6 with no right boundary. So we are looking at